Yeah, good evening, everybody. Good evening. Good evening, professors.
Yes.
Yeah, researchers and students, and our delegates, those who are registered for the program and waiting for attending this program. Very good morning to all. In fact, today, in connection with our department's Platinum Jubilee celebrations of this year, 2020, we are conducting the lecture series. This is the second lecture series in the series, and we are very lucky to have a great professor in the area of design of experiments. Professor D.K. Ghosh is FRSS UK, FGSA Gujarat, UGC BSR faculty fellow, and he is the former professor and head, and in fact the founder head professor and head of the Department of Statistics, Saurashtra University, Gujarat. He is the member of several committees, and he was the syndicate member, Senate member, academic council member, and several other bodies also. In the university as well as outside, we met regularly in several places, in UPSC advisor and several. Above all, he has published more than 150 publications in the area of, especially in the area of design of experiments, and published several books to his credit. Also, it's a very very important to say that he has supervised several PhDs, doctoral theses, more than 45 theses, to my knowledge. And he's a reviewer of several international journals and a member of several international committees. With your permission of the group of audience, and on behalf of the Department of Statistics, I'm very much happy to invite Professor D.K. Ghosh to this program, and to introduce Professor, in fact, this program. I'm very much happy to be, we are very lucky to hear he is talking about balanced designs. Is a very giant in the area, and let us wait for his nice presentations and talk. Professor, please consider the from the beginning stage, because some of our students are also eagerly waiting for your talk. And with the bless of our former professors and our Gurukans, I invite you, Professor, welcome you, Professor, to this webinar, this international webinar, in fact. Thank you all. Please, shall I hand over this mic to Professor D.K. Ghosh? Please, Professor, please start your presentation. And
thank you. First of all, I am very much thankful to Professor Satish Kumar, who gave this opportunity to me to share some of my contribution in design of experiment with all of you. I'm also thankful to all the faculty members and the concerned person of this conference or a series of lectures talk. So let us start our talk without wasting our time. See, actually, design of experiment, the balance is a very important point. If the design is not balanced, then it is very difficult to estimate the, you can say, parameter or treatment effects. Sometimes a design may be partially balanced, then somehow one can manage. But if this ignore these two, then we cannot either estimate the treatment effect or analyze the data. So this we can say that balanced is the backbone of the design of experiments. So let us first start a definition, because I have to take care of MSc student also. So a block design is said to be balanced if all the treatment effects have same variances. See, I forgot to explain block design. Any design is a block design if V treatments are arranged in B block and each block have Kj treatments where J is equal to 1 to B, and each treatment is replicated Ri times where I is equal to 1 to V. So this arrangement of any design is called block design. So later on we'll tell you the block design is either complete block design or incomplete block design. I'll tell you later on. So here I say that Ti is a treatment effect and Tj is also treatment effect, but I is not equal to J, and both are ranging from 1 to V. So Ti minus Tj is a treatment effect. If you want to know variances of Ti minus Tj of all the treatment 1 to V, and if gives K times sigma square, K is a constant and sigma square is error means sum square of invertible. Again, we want to say that block design is also said to be balanced if all the treatment effects are estimated with same precision. Precision means that is, if you take the ratio of 1 by variances, that is called the precision of all the amount, Fisher's amount of information, we can say. One of the most important and easy example of balanced design, which is belonging to the block design, is balanced incomplete block design. Short form we call BIBD. Now, there are 3 types of balanced design so far, which are called variance balanced design, efficiency balanced design, and pairwise balanced design. Now, I want to inform this in the form of matrix. See, a C matrix is called the information matrix of a block design, and C can also be obtained as diagonal of R1 to R1V matrix minus N capital K inverse N prime, where diagonal of R1 R2V is the replication size of V treatments, N is the incident matrix of block design, and K inverse is the reciprocal of sizes of the block size, and N dash is the transpose of incident matrix N. And after that, incident matrix N is equal to Nij is equal to 1 if ith treatment occur in the jth block, equal to 0 if ith treatment do not occur in jth block. So with this, if I want to find out the C matrix of any block design, and if I can write it in this form, where diagonal elements are all A and off diagonal elements are all minus B, and if I say all the off diagonal elements are plus A, it must be 0. Means each sum row and each sum column must be 0. And because of this, the C matrix is called doubly centroid matrix. Now, I can write down C matrix in this form also. If I add A with B, A plus B, and that is the IV is the identity matrix minus B, EVB. EVB is a matrix of unity with V rows and V column. But during 58 era, there was no actual idea of how to find out the C matrix in terms of eigenvalues for the balance design. So 58 Rao defined that block design is a balance if C is equal to theta IV minus 1 by V EVV. But theta is a eigenvalue, non-zero eigenvalue with multiplicity V minus 1 because one eigenvalue is 0. That's why the C matrix is also called positive semi-definite matrix because one eigenroot is 0 and remaining eigenroots are positive. So variance balance, now I want to define the variance balance. A block design is said to be variance balance if C matrix is expressed as C is equal to theta IV minus 1 by V EVV. Now you can check the C matrix of balance incomplete block design and variance balance design, both are same. So one can say that balance BIBD and variance balance design in terms of C matrix is same. Also we can say that BIBD belongs to the variance balance design. The difference is that the balance incomplete block design is always binary, proper, equireplicated. While it is not true for the variance balance design. It may be equireplicated and proper, unequal replicated, non-proper, maybe binary, maybe non-binary. Again, there is no parametric relation for variance balance design. While for balanced incomplete block design, there are parametric relations. That is, VR is equal to BK, lambda times V minus 1 is equal to R times K minus 1, and B block is always greater than equal to treatment. So because of this no condition on the variance balance design, the variance balance design is very simple and easy to obtain and easy to analyze and has more application because the BIBD is not available for all the parameters. Now one can also define variance balance design if it permits the estimation of all estimable normalized treatment contrast. I want to say a normalized treatment contrast with the same variance, that is variance of Ti minus Tj is equal to K times sigma square for all I equal to J is equal to B, then also it is called the variance balance design. Now one point must we read, this is coming under the properties of block design, which I am not taking here. Every block design must be connected. If design is not connected, then we cannot estimate again all the treatment effect. We can estimate some, but not all the treatment effects. Now, when you can say the block design is connected, so you have the C matrix, you estimate the rank of C matrix. If the rank of C matrix is equal to V minus 1, exactly V minus 1, then your block design is connected. Otherwise, it is disconnected. And treatment effect cannot be estimated for the non-connected design. So whatever design I am discussing here, all are connected design. Again, somebody has also advocating that for a block design, if you can write down C matrix in the form of A minus BI plus BJJ prime, where AB are constant and I is an identity matrix, J is a vector of all elements 1 and J dash is a prime of the G. Then that case also the design is a variance balance design. This shows that the diagonal element A minus B is always a constant and it is positive and all are equal. Finally, for any block design, I think any block design I am telling you, they are defining concurrence matrix Nn prime. So Nn prime is equal to R minus lambda IV plus lambda Jj prime, where lambda means a pair of treatments occurs together in lambda blocks. This is true for balance DIBD, variance balance design, and also I will discuss later on pairwise balance, not true for the efficiency balance design, which I am discussing. So this is an important factor for variance balance design and also the balance incomplete block design and variance balance design. See what happens, block design is connected and we are estimating the treatment effect. And then we compute the variances of all the treatment effect. We found that for some of the treatment effect, variance are K1 times sigma square. For some other treatment effects, variance are K2 sigma square. It is all the variances are not equal. So how we can say? Then they said, okay, if variances are not equal, let us see whether efficiency are equal. And efficiency here is declared, designed as the ratio of the two variances. One is the original variances which we are computing, and other is a variances of considering this design as a randomized block design. So because of this idea, they discussed and investigated efficiency balance design. The 2-3% were the actually introduced the design. One was the Tocher, 59, and then after that, Nigam and Puri introduced this design. Then Tocher discussed in 59, but Nigam and Puri discussed in 75. This paper has published in Sankhya and also in JRSS. We have also done a lot of work in this balance design. We'll see later on. So a block design, which is defined as DVBRK. Here lambda is not important. That's why lambda is not included. Is said to be efficiency balance design if all the V-1 treatment contrast or contrast or effect both are same, there's no difference, such that M0 S is equal to mu S, where M0 is a matrix, S is a vector, mu is a vector of efficiency, and S is already vectors. If mu is unique non-zero eigenvalue and all the mu are same with multiplicity V-1, then they say that block design is a efficiency balance design, not the variance balance design. Now, if this M0S by equal to MS, it was very difficult to estimate the mu. So later on, Jones also defined 59 two different M0 matrix. He defined M0 is equal to mu times I minus 1 R prime by N, where I is an identity matrix, R is a vector of reflection size, and it is a transpose. So it is a now row vector, not the column vector. And N is a total number of units, that is B into R or B into K. Again, he defined another way, the M0 matrix. This is equal to R inverse, capital N, K inverse, N prime. R is a reciprocal of the repetition of our treatments, the repetition size. N is a incidence matrix, K inverse is a reciprocal of the block sizes, and N is a transpose of incident matrix, and that is one address I have already defined. Now, equating these two matrices of M0, one can say mu I this is equal to this. So now I have all these values and I have all these matrix or vectors. So equating this, we can obtain the mu means efficiency. So this way, efficiency of the M0 matrix are computed, and if it is same of all the treatments with multiplicity V minus 1, we say design is a efficiency balance. Next, we discuss general efficiency balance design. Of course, there was a lot of controversy over efficiency balance design and general efficiency balance design. Finally, this problem was solved by Kageyama and Rahul Mukherjee once, and again Kageyama and Sudhir Gupta. Both have solved this problem. So Das and Ghosh, this paper is published in Sankhya. I think it was my first paper in Sankhya. And we defined a general efficiency balance design for some eigenvalue theta, where S1, S2, B, it is actually that is proportional to the replication size. There I took R1, R2, RV. I am taking proportional to R1, R2, V as S1 to AV. And if A matrix, if I can write in this form, A is equal to theta S minus G inverse SS prime, where S is equal to diagonal of S1, S2. There was diagonal of R1 to RV, but and S is a replication vector. This is criteria. S prime 1 is a G. So G is a here is nothing but the total number of units. This is S1 plus S2 plus SB, that is total number of units. Now, here we also define that how the general efficiency balance design becomes the variance balance design. So if S is equal to R, then the block design, which I define as a general efficiency balance design, becomes efficiency balanced. However, if all S is equal to 1 or all equal, S1 is equal to S2 is equal to SB, then the design becomes variance balance design. So from the general efficiency balance design, we have defined all the parts. And the analysis of general efficiency balance design is very straightforward and very easy, because the generalized inverse of A, because this is a C matrix, it's a matrix is a similar matrix. If it is similar matrix, we cannot estimate it, we cannot invert it as A, so we have to imply the generalized inverse of matrix. That's why its generalized inverse of matrix A will be very easy, as this is a idempotent matrix. And if it is an idempotent matrix, that's very easy to estimate, take the generalized inverse of A as a, generalized inverse of A is equal to theta inverse and capital S inverse. While the adjusted treatment sum square, one can also obtain by Q prime S inverse Q prime by theta, where Q is a adjusted, non-adjusted treatment total. Then we come to the another balance design. I will come to later on construction also, pairwise balance design. Let us define it. An arrangement of V treatments in V block is defined as pairwise balance design of index lambda C. So far, in other design, we are telling lambda is a pair of treatment occurs together lambda block, but pairwise design we call lambda index. And this type of design is defined as V, K1, K2, K3, Km. Let us see the difference between other design. There we are defining V, K, R. But here we are defining K1, K2 because in pairwise design, replication size is always same, but K1 block size is always different. But recently, we have constructed some pairwise balance design where R is also unequal. That is two types of representation size. And I think Rajaratnam is sitting there. In one is paper published, there is also unequal representation size of pairwise balance design. But literature so far, all the pairwise balance design obtained is with only equal replication, not unequal replication. Then second condition is that each set contains these symbols. Symbols mean block sizes that are all distinct. This may be two types or three types, but not all same. If they all are same, that may not be the only pairwise balance design. At least there are two types of block sizes. And third point is Ki is always equal to V. V is the number of treatments, Ki is the block sizes, and Ki is not equal to Kj. Last point, every pair of distinct treatment occurs in exactly lambda sets of the design. And apart from all these conditions, some more parametric relations are imposed here, because balance incomplete block design has parametric relation, variance balance has not more, so more, but pairwise balance design has very important parametric relations. The first parametric relation is B is equal to summation Bi, I is equal to I to 1. Here M denotes number of blocks. Second is lambda times V is equal to V times V minus 1 is equal to summation Bi Ki into Ki minus 1, I is equal to 1 to M. So for pairwise balance design, this two condition, that is parametric relation, must satisfied. Now there was very problems for the pairwise design to compute C matrix, because almost all design we are obtaining either C matrix or M0 matrix. But pairwise design, it is not possible to compute C matrix because of the different block sizes, and lambda are also different. So we have finally decided that it should be find out the concurrence matrix n dash. That is, if all the off-diagonal elements of n dash matrix are same, is constant, then that was the characterization of the pairwise balance design along with these parametric relations. What is characterization of same earlier as you have seen? R minus lambda IB plus lambda 1 into 1 prime. Now, MSc students are also there. I want to define a very good criteria called Galois field or Galois field. So with the introduction of Galois field, several problems in design of experiment, coding theory, number theory, combinatorics theory are solved, which were unsolved. It was very sad. I'm not going to tell the story of Galois, who died at very early stage, I think 21 or 22 age. So what is a Galois field? A field is said to be Galois field if it is closed under the operation of addition, subtraction, multiplication, and division. Also, if it is satisfied n is equal to r mod 2. For example, if take 7, 7 is equal to 2, because if I divide by 7 by 5, the remainder is 2. So that's why 7 is equal to 2 mod 5. See, when he introduced this Galois field, people were telling how 7 is equal to 2 mod 5. It's foolish. But his result was solved many problems. So n number, r remainder, and d divisor. So now what will be the elements of Galois field S? So elements of Galois field S will be always starting from 0, 0, 1, 2, 3, S minus 1. And where S is either prime number or power of the prime number or product of the prime number or product of the prime and power of the prime. But for that, he discuss how to obtain the element of Gauss field S in terms of primitive element, and obtaining the primitive balance, many more problems can be solved. I am taking an example that S is equal to 7. 7 is a prime number. The element of 7 are 0, 1, 2, 3, 4, 5, and 6. Let us see how this element follows the rule of Gauss field 7. What is rule? Rule A is that if you select any element which are belonging to Gauss field 7 and perform any one of the operation, addition, subtraction, multiplication, and division, then the resulting elements all are distinct, and all the elements will belong to again the same element of Gauss field 7. That is, it will be again the 0, 1, 2, 3, 4, 5, 6. If they are not, then that element is not the Gauss field. So, for simplicity, I have said select any element from the GF7 and compute the power of all the S-1 element with the selected element. Again, it gives all the distinct element. Further, if let us say one element is A raised to S-1 is equal to 1 reduced mod 7, then such element A is called primitive element. And primitive element will be helpful in the construction of the so many problems. Let us see a rule one by one, how it follows all the rules. This is for MSc student. Please take care of this. Let us select an element 5, which belongs to GF7. This element follows the operation of Gauss field as first is addition. Let us select first element is 0. 0 plus 5 is equal to 5. 1 plus 5 is 6. 2 plus 5 is 7. But 7 is not the element of GF, but 7 is equal to 0. Because if divide 7 by 7, remainder is 0. 0 mod 7. 3 plus 5 is 8. 8 means 1 mod 7. Divide 8 by 7 is 1. 4 plus 5, 9. 9 is a 2 mod 7. Next 4 is 5. 5 plus 10 is 3 mod 7. Then 6. 6 plus 11 is 4 mod 7. So let us see. All the elements are here. 5, 6, 0, 1, 2, 3, and 4. All the 7 distinct elements are there by adding different element with the only 5. Again, you take subtraction. 0 minus 5 is minus 5. How I can write minus 5? Minus 5 because 0 minus 5. And 0 is equal to 7. Because 7 divided by 7 is 0. 7 minus 5, so it is a 2. 1 minus 5 is minus 4. Equal to 0 minus 4 equal to 7 minus 4 equal to 3. Then 2 minus 5 is equal to minus 3. So minus 3 is equal to 0 minus 3 is equal to 4. 3 minus 5 is equal to minus 2. So 0 minus 2 equal to 7 minus 2 equal to 5. 4 minus 5 is equal to minus 1. Minus 1 equal to 0. Minus 1, sorry, minus 1. So 7 minus 1, 6. Then 5. 5 minus 5 is equal to 0. Last 6. 6 minus 5, 1. So all the elements 0, 1, 2, 3, 4, 5, 6 have come there. It's all distinct elements. Similarly, multiplication. 0 into 5, 0. 1 into 5, 5. 2 into 5, 10. 10 means 3. 7 divided by 10 is remainder 3. 3 into 5 is equal to 15. 15 is equal to 1 mod 7. Then 4. 4 into 5 is 20. 26 mod 7. Then 5. 5 into 5 is 25. 25 is 4 mod 7. Then 5, next 6. 5, 30. 30 is a 2 mod 7. All the elements 0 to 6 has come there. Next is division. 0 by 5, 0. 1 by 5 is now here is the problem. So what I can write 0 plus 1 by 5, and I can write 0 is 2 into 7 because 7 is 0. So 2 into 7 means 14 plus 1, 5. So 15 plus 5 is now 3 mod 7. 2 by 5. 2 by 5 I write 0 plus 2 by 5, and 0 I am writing as a 4 into 7 plus 2. So it is 28 plus 2 means 30. 30 by 5 is 6. Now 3 by 5. So 0 plus 3 by 5. 0 I am writing 1 into 7. 7 plus 3, 10 by 5 means 2. Then next 4 by 5. 4 I am writing 0 plus 4. Or 0 I am writing 3 into 7 plus 4. So 3 is 21 plus 4. 25 by 5 is 5. I am writing 5 by 5 is equal to 1. 6 by 5 is equal to 2 into 7. 7 is a 0. So 14 plus 6. To 14 plus 6, 25, 4. So you see all the elements 0, 1, 2, 3, 4, 5, 6. It means the Gauss field obey all the operation of addition, subtraction, multiplication, and division. Now I am showing you one example of this. So let us take same element 3 to find out the primitive element. So I am taking 3 raised to 7 minus 1, because 7 was the element of Gauss field. So 3 7 minus 1 means 3 raised to 6. If 3 raised to 6 is equal to 1 mod 7, then 3 will be the primitive element of Gauss field 7. Let us write down 3, 3, 3, 3, 3, and power will be all its element. 3 0 is also there, 3 0 is 1. So 1, 2, 3, 4, 5, and 6. 3 1 is 3. 3 square means 9. 9 if you divide by 7, it is a 2 as a remainder. Now 3 cube is 27. 27 is equal to, divide 27 by 7, the remainder is 6. But I have found a very simple and shortcut method. What is shortcut method? Shortcut method is 2 into 3 is 6. Now 6 into 3 is 18. No need of finding 3, 4 is 81. And 81 is a remainder is 4. Now 4 into again 3 is 12. No need of finding 3 is to 5. And 5 into 3 is 1. 5 into 3 is 15. 15 means 1 mod 7. So I got it 3 raised to 7 minus 1 is equal to 1 mod 7, hence 3 is a primitive element of GF7. Let us verify whether there are more than one primitive element for any Gauss field. 2 is the same. 2 raised to 1, 2, 2, 2 cube, 2, 4, 2, 5, 2, 6. So 2 square is 4. 2 cube is 8. 8 means 1. So 2q is also 1, hence means 2 is not the primitive element of Gauss field 7. Let us take again 5. So 5 1, 5 2, 5 q, 5 4, 5 5, 5 6. 5 1 is 5. 5 square 25 is a mod 7 is 4. 5 q means this we can say 4 into 5 is 20. 20 is a 6 mod 7. 6 into 5 is 30. 30 is a remainder is 2, so 2 mod 7. 2 into 5 is 10. 10 is a 3 mod 7. 3 into 5 is a 15. So we found it that 5 raised to 6 is equal to 1 mod 7. What it suggests? It suggests that there may be more than one primitive element for Gauss field S. Now let us see its application for the construction of mutually orthogonal Latin square design. Now let us first define what is Latin square design. A block design is called a Latin square design if it has S square treatment arranged in S rows and S columns, where each row contains one treatment, distinct treatment, and each column also contains each distinct treatment, and each Latin letter also contains a distinct treatment. I have not shown example here, but this is called Latin square design. And then after that it's called orthogonal Latin square design. Now you take two Latin square design, both have of same size. Suppose it is a S cross S. Superimpose one Latin square design on the other Latin square design. If every pair of treatments occurs once and only once in whole design, then that is called orthogonal Latin square design. Now say we have more than two Latin square design, 3, 4, 5. So if all the two Latin square design are orthogonal, means every pair of Latin square design are orthogonal, then all such orthogonal Latin square design are called mutually orthogonal Latin square design. So let us, we say that S1, either I construct S is a prime number, S is a complex number, means power of the prime, or S is a product of the prime. Let us come for case 1. What will write? Write the element of Gauss field from 0 to S minus 1. Take any one element and find out its primitive elements. And after writing primitive element, keep all this element in a row and call it as a key row. Again also all this element keep in a column and call this as a key element, key columns. And after that, derive the key element with reduced mod to obtain the orthogonal Latin square design. Let us see here. First, a simple example, I am doing 3. 3 is a prime number. The element of 3 is a 0, 1, 2. So 2 is a primitive element of J3. Now take all power 2, 0, 2, 1, 2, t. 2, 0 is equal to, suppose I am not taking 2, 0, it is a mistake, I am taking 0 only. Because element 0 is also one element. 2, 0 is already 1 here. 2, 1, 2 and 2 square is 4 is for 1. So I have taken 3 elements 0, 2, 1. There is only 3 elements of Gauss field 1, 0, 1, 2, not more than that. But I am writing this in this fashion. Same, it is a column also 0, 2, 1. Now say 0 plus 0, 0, 0 plus 2 is 2, and 0 plus 1 is 1. 2 plus 0, 2, 2 plus 2, 4. No, because our S is 3. So if divide 4 by 3, remainder is 1. Similar 2 plus 1, 3, remainder is 0. 1 plus 0, 1. 2 plus 1, 3 is remainder is 0, 0. 1 plus 1 is 2. So this is a one Latin square design. I want to take another Latin square design. So I will keep what? The first key column second same, but the next 2 key column I will change it. So 1, 2 will be 1, 1 will be 2, and I will operate the same operation. I am getting this orthogonal Latin square design. So 1 and 2, so we have 2 Latin square design. So they are 2 orthogonal Latin square design. But verify it, whether it is true or false. So I am superimposing this Latin square design over this Latin square design. What is happening? 0, 0, 2, 2, 1, 1, 2, 1, 1, 0, 0, 2, 1, 2, 0, 1, and 2, 0. So all are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2, 2, 0, 2, 1. And so all the pair of treatments occurs once only. That's why this is a orthogonal or mutually orthogonal lattice square design. Now I am leaving 5 because time is not there. So I have to cover this way. You can 5 is for 5 2 is a primitive element. You can find out the Gauss orthogonal lattice. One thing I want to say, see, if your size is S, there will be always S minus 1 mutually orthogonal lattice square design. That's why we have 1, 2, 3, 4 mutually orthogonal lattice square design. Similarly, you can find out of 7. This is 7. This is 1, 2, 3, 4, 5, 6. Now the case 2, which is very important, where S is a complex number. Complex number is a power of the prime number or product of the prime number. See what Gauss found, if S is a complex number, then the Galois field of operation addition subtraction follows, but multiplication does not follow. If multiplication does not follow, it means division will also not follow. So what he did something different. He introduced one function which is called minimum function, and minimum function was obtained by using a polynomial function, those polynomial functions which are irreducible function, and irreducible function is called as a polynomial function. So what he did like that he defined a function alpha 1, a1 into alpha raised to n, a2 alpha raised to n minus 1 plus dot alpha n. What is a1, a2, n? a1, a2, n are element of Galois field S is equal to p raised to n, where p is a prime number and n is an integer, and alpha is a primitive element of Galois field S. So using this thing, he said, if I can write down alpha raised to pn minus 1, which reduce mod p raised to n, then that alpha is a primitive element of Galois field S. I am not discussing, I'm just direct, I go to the their example. So let us take example 4, 1 and 8 I will take. So I have S is equal to 4. So 4 is equal to 2 raised to 2. So 2 is a prime number and this 2 is a integer. So element of Galois field are not 0, 1, 2, etc. but 0, alpha raised to 0, alpha raised to 1 and alpha square. So here we do not go more than 2, means more than 4 minus 2, that is n minus 2. This is already explained you. Now let us take the polynomial. A1 alpha square plus a2 alpha 1, a3 alpha 0. I consider I have to find out this function in such a way that this is a irreducible factor. We cannot get factorized. So you can take any value of a1, but a1 may be only s is equal to 2, either 0 or 1. a1, a2, a3 will be either 0 or 1. I am taking all value 1. So what is happening? It is 1 into alpha square plus 1 into alpha plus 1. So alpha square plus alpha plus 1. And this is a not factorizable. So this is a irreducible polynomial, or we define it as a minimum function. Now using minimum function, we can find out primitive element in this way. So I take alpha, primitive element, alpha, and power 0, 1 and 2. Not more than 2, not more than n minus 2. n minus 2, 4 minus 2 is 2. So s minus 2, sorry. So it is a 1, alpha 1, 1, alpha square. How alpha square is alpha plus 1? So what we are doing, so alpha square, if you add this alpha square, it is becoming 2 alpha square plus alpha plus 1, and 2 is equal to 0 because s is equal to 2, so it is alpha plus 1. So alpha square is equal to alpha plus 1. Now alpha q is equal to, how I can define alpha q is equal to alpha into alpha square. Alpha square is alpha plus 1, I have already found. It is alpha into alpha square plus alpha. And alpha square is equal to alpha plus 1 plus alpha plus alpha, 2 alpha plus 1, and s, 2 is s, so it will be 0. So it is only 1, so alpha q is equal to 1. So alpha q1 means alpha raised to pn minus 1 is equal to 1. So alpha is a primitive element of Galois field 4, which corresponding to minimum function alpha square plus alpha plus 1. With this idea, let us construct a orthogonal lattice square design from here. So our elements of GF are 0, 1, alpha, this is already, and here I have no time, otherwise I have already explained you how division and multiplication are obeying in complex numbers. So let us obtain the mutually orthogonal lattice square design. So this is the element 0, 1, alpha plus 1, and this is a column, row, this is column. The same way we add 1, 0, 1 plus 1, 0, 1 plus 1, 2, 2 is 0, S2, this alpha plus 1, alpha plus 2 means only alpha 2, 0, alpha plus 0, alpha, alpha plus 1, alpha plus alpha 2 alpha means 0, alpha plus alpha 2 alpha 0, only 1, alpha plus 1, alpha plus 1, alpha plus 2, only alpha, alpha 2 alpha means 0, this is 1, and alpha plus 1, alpha plus 0. So what is happening? Now we got this design. So I have 1, 2, and 3 mutually orthogonal lattice. This way we can also find out for S, but very difficult to find out the primitive element and the minimum function to and the element. Time is not. I have explained so many things. So this way we can say Gaussian field of S. Similarly, we can find out 9 also. This is 9 also. If you have product of number, the product of Gaussian field is very interesting. So you have 6 is a product of Gaussian numbers 2 and 3. So write down element of 2. 2 is 0, 1 and 3 is 0, 1, 2 and take all possible combinations. This is the element of what is called 3, 0, 0, 0, 1, 0, 2 and this is a 1, 0, 1, 1. It is not important. So like this 0, 0, 0, 1, 0, 2, 1, 0, 1, 1 and 1, 2. 6 possible combinations. So this is a row and same column and same thing operated. Only consider that the first will be with reduced mod S2 and second will be reduced mod S3. For example, here I want to 1 and 1. 1, 1 is, there is a mistake sum. 1, 1 is 2. 2 means 0 because S2 is 0. So 2 plus 2 is 4. 4 means divide by 3. So it is a remainder 1. So it will be 1. So like this, we can obtain for 6. I'm not going to it. I want to explain the general efficiency balance design, which is very much important for me. I'm reading all these things. I was thinking to obtain one more, what is called balance in complete block design from same Gaussian field. After that, so I have the V is equal to, I have a parameter V is equal to 4 lambda plus 3, B is equal to 4 lambda plus 3, R is equal to 2k plus 1, K and lambda, any lambda. If put R is lambda 1, I get parameter as V7, B7, R3, K3, lambda 1. And this 4 lambda plus 3 is a, what is called prime numbers. So if it is a prime number, so I can use the Gaussian field, and within the Gaussian field, that it is a 7, same way, element 7, we want to the Gaussian field, 3 raised to 6 minus 1 is a, what is called 1. So 3 is a primitive element of Gaussian field. This, what we do, here I have a even number of power and odd number of power. So either take even number of power or take odd number of power. And taking even separately, odd number separately, and develop it with reduced mod 7, we get 2 types of BIBD. But so I have taken odd number, power 3, 1, 3, 2, 3, 5. So if you solve it, it is 3, 3 and 5. So reduce, develop it, 3, 4, 5, 6, 7. 8 means 1, because 8 divided by 7 is 1, 2. Now 6, 7, 8 is 1, 2, 3, 4, 5. 5, 6, 7, 8 means 1, 2, 3. And checking is 2 and 3, checking point. 5 and 6, 4 and 5. So this is the 7 blocks with B is equal to 7, R is equal to 3, K is equal to 3, and each pair of pigment occur together in one time. Let us take the 1 and any element, 4, 7. So 4, 7 is occurring only one time. So this is a BI 1 to 1 time. Now take even number 3, 2, 3, 4, 3, 6. If you develop it, reduce mod 7, we got this element, develop it 2, 3, 4, 5, 6, 7, 1, 4, 5, 6, 7, 8 means 1, 2, 3, 1, 2, 3, 4, 5, 7. And this is a BIBD. Similarly, one can do for 11 also, and 11 2 is the primitive elements. And later on, myself and Biswas in 2002, we published one paper in, I think it was applied statistics. If I combine these two BIBD of this type of series, we get another BIBD, and we call it a doubly balanced incomplete block design. Now, analysis part, I cannot go through it. But one thing is that after finding the construction, everyone must check the C matrix. This is C matrix, and C matrix, if in this form, then we can say this is a balanced design or BIBD with this eigenvalues. Next was variance balance. I'm all omitting. I want to say only one example of general efficiency balance design, which is introducing in another way, because timing is not permitting me. And one more theorem, just last year I have developed for any variance balance, efficiency balance, or general efficiency balance, that for V, B, Ri, Kj, and lambda, theta is equal to VCIM. See, earlier we are finding always theta is equal to by using the C matrix. Here we saw a shortcut method. No need of finding C matrix. Without C matrix also, where one can find out the eigenvalues. And this V is a treatment, and CIM, I have defined it this as a product of Nij, Nmj upon Nj, where I and M are treatment, and I not equal to M, and N dot is a block size, and J is varying from 1 to B. Proof, I am not giving you proof, but example I can show you. So this is a balanced incomplete block design, and if solve C matrix, we are getting C equal to 4 by 2. But if you use our just now developed method, C is equal to B times CIM, B is equal to 4. And this is a design where lambda is equal to CIM. This CIM means nothing but lambda. Lambda is 1. So it is a entire K, 1 by 2. Same 4 by 2. So without solving C matrix, I can find out the theta eigenvalue also by simple my method. So also, once you got the construction, we got the analysis, everyone must find out the variance of the treatment effect. If the variance of the treatment effect is equal to 2 by theta sigma square, then it is your variance balance design. Then find out efficiency factor for every design. Efficiency factor is nothing but it is a ratio of the two variances, where one variances is considering the design as a resulting design as a randomized block design, and the denominator is a resulting design, that is which design you are finding. And R is a ratio, and if you solve this ratio, for that example I have solved, I got E is equal to 0.62, and E is always less than or equal to 1. As much near to 1, it is that much more efficient the design. Optimality, after that, one must check the optimality. If you want to do some research work in design experiment, after finding efficiency, we go to the optimality of the design. So all I am operating, this is time consume. And this I want to, I may take some 10 minutes more, but this I want to explain in another way. So I explain you efficiency balance design, that it is, I have to obtain the M0 matrix of two types, and we have to equate and then find out the mu. And also, I also way to find out A matrix, S inverse, S minus, S dash prime, etc. So it was very difficult, but I found a very shortcut method to find out efficiency balance, variance balance, and general efficiency balance. In this method, since this was earlier developed by Puri and Nigam and other persons, and equating these two, I am getting mu. But what I did a simple idea, that CIM is equal to CSISM, where C is a constant or proportionality. The efficiency factor for such a design is C times summation Sn, M is equal to 1 to B. See, since this criteria or this research does not involve much more mathematics or matrices, so the people are not accepting for publication, because for paper publication, they now need editor or associate editor. It should be full of mathematics. That's why this method I am not using always, rarely use. I use the all earlier method, but this is a very simple, easy method that I want to explain you. First, I take an example, then I will come to the theorem. This is an example. I have taken a variance balance design VB7 RK2 lambda 1, which I have already explained you earlier. This is for research person who want to do some research. So already I have explained construction. This is a BIBD. This is first block, second block, third, fourth, fifth, sixth, 7 blocks. And this is their incident matrix N. Means here is a 1 to 7 treatment and 1 to 7 blocks. Now 1 is present, so it is 1, 2 is present 1, 3 is not present 0, 4 is present 1, and 5, 6, 7 is not present, so all 0. Similarly here, 1 is not present 0, 2 is present 1, 3 present 1, 4 not present 0, 5 present 1, and 6, 7 not. Like this, for all the blocks, I found the incident matrix, which is binary, because binary means the element must be either 0 and 1. So this is my, and I am adding one more treatment here. That is 8 treatment. Here it is not shown, but one last 8 block I am augmenting. One block is augmented where each treatment are there. All 8, 1, 2, 3, 4, 5, 6, all 7 treatments. So naturally, here first block also 7 treatment, 8 treatment. So it is 1, it is 1, it is 1, it is 1, 1, 1, 1, 1. So what is block size now? 3, 1, 4, 3, 1, 4. All the block size now is 4. What is reflection size? 1, 2, 3. All the reflection size 3 up to 1 to 7. But this is not 7. This is a 3. This is 1, 2, 3, 4, 5, 6, 7. So the reflection size for treatment number 8 is 7 now. So let us see whether it is efficiency balance design or not. So what is our idea? Our idea was a constant C1 into S1 into S2 is equal to summation Nij into Nmj by N dot j. Means Nij Mj means this into 1. 1 into 1, 1 by 4, 1 by 4. This is 0, this is product 0, product 0, product 0, product 0, product 0. So it is 1 by 4. You take any element first and 7 block. 1 into 0, 0, 0, 0 into 0, 1 into 1, 0, 0. So it is again 1 by 4. So C1 into 3 into 3 equal to 1 by 4. But if you take the last element, 0 into 1, 0 into 0, this is 1, 1, 1. Means it is a 3 by 4. So shortcut I can say for treatment, product of first treatment, which is any treatment up to 7, it is a lambda by k plus 1, and treatment 1 with block size, with treatment 8 is this is R, 1 to R by k plus 1 for treatment 8. Let us write down this in this fashion. So I got C1 into 3 is equal to 1 by 4. So C1 is equal to 1 by 36. 9 plus 30. C2 into 3 into 7 was 3 by 4. So C2 by 7 by 3 by 28. Now, it will be a efficiency balance design if C1 is equal to C2. But it is a 1 by 36, it is a 1 by 28. So they are not equal. So this is not efficiency balance design with blocks efficiency size 3, 3, 3, 7. But now check for general efficiency balance design. What I will do, the last treatment 8, which efficiency size was 7, I consider it is the S0, not the 7. So our 3 into 3 is same, but C2 into 3 instead of 7, I took efficiency size S0. So it is now C2 is equal to S0 by 3 by, what is called? 3 cancel, 1 by 4 times S0. Now C1 is equal to C2 means what will happen? 1 by 36 is equal to 1 by 4s0. So s0 is equal to 9. If I put 9 in place of 7, we are getting general efficiency balance design. So this was like that. I added one treatment here, and instead of 7, this is one treatment added here, I have not shown. Here it is 9, so this will be a, what is called, general efficiency balance design. So when we are not able to get efficiency balance design, we are getting general efficiency balance. One more example, I am taking here, I am not adding extra treatment, but I am adding extra blocks only, where all treatments are there, see 1, 1, 1. So now block size is, so it is not 3, 4, it is, by mistake, it is 1, 2, 3, 4, it is 4. So what is happening? 1 by 3 and 1 by 4. So all, see 1 by 3 and 1 by 4. So here we can see all the C1 are Ci is equal to all Cm. So it is a variance efficiency balance design as well as the variance balance design, general efficiency balance design. I want to explain one thing more here. Till after that, one criteria was proved that there are 3 types of properties. If design is a variance balance design, if design is a equirepeated design, if design is a efficiency balance design, if any of the two criteria are satisfied, third criteria automatically fulfilled. What is meaning? Suppose a design is a equireplicate and variance balance, it will be efficiency balance. If a design is a variance balance and efficiency balance, it will be an equireplicate design. This I want to show from here. So all reflection size is equal 3, 3, 3, 3. So it is a efficiency balance design. It is a general efficiency balance design. It is also a variance balance design because all reflection sizes are equal. Another thing, another criteria. See, it is a 1 into 1, 1 lambda and plus 1 into 1 also 1. So how much? 2. So summation Nij into Nij for any pair of 2 treatment is a 2y, only 2. So this design is also a pairwise balance design. So if I put it in the form of NN dash matrix, it will be always R minus lambda, R is 3, 3 minus 2, identity matrix plus lambda 2 EBB. So we can see here with one example, I am showing you it is a variance balance, it is efficiency balance, it is general efficiency balance, it is a pairwise balance design. So far only 3 balance design was available. I added one more balance design that is called general efficiency balance design. So I cannot give you some more examples. Here also I have taken, there is a block size is different, here size equal, different. This is 5, 5, this is different. I have added 2 blocks. So adding this 2 blocks, you can find out, again this is a efficiency balance design and as well as general efficiency balance design. But since representation sizes are not equal, R1 is equal to R2, not equal to S, so it is not a variance balance design. And same way, it is not the pairwise balance design. So I have no time, Satish. If you give me, this was a general I found. If you give me another day also, I can explain you so many things. I have for MSc students, PhD students, etc., etc. Finally, I'm showing you some references. This is references mine. This is my references. So thank you very much.
Thank you, Professor. In fact, a lot of things are there. And in fact, one more hour needed, I think so.
I think you give me 2, 3 more days.
Yeah, we can find some more time later.
Because I have not covered balancing complete block design. I have not covered partially balanced. I have not covered so many things.
Yeah.
No, I'm not covered. So this is just an idea I have given.
Okay, Professor. Okay. And now this some. I think anyone can.
Questions? Yes, questions.
Any questions or any?
Yeah. Any queries? Anything, sir?
Yeah. Anything. we can discuss sometime.
I took more time. I'm sorry for that.
Yeah, I taken, yeah, no, doesn't matter, sir. It's a, please, several experts are there.
Good evening.
Good evening, Sadish
Yes.
and friends. Highly excited and delighted to attend this lecture after 20 years of
Thank you,
retirement.
sir. Thank you very much.
And,
Thank you very much, sir.
and I'm really feeling nostalgic.
Oh,
I now think, why not I come back and take a course under you?
yes, sir. Yes,
With
sir.
Galva Field.
Thank you very much, sir.
See, those days we were given to understand design not in this way, the very conventional methods.
Yes,
And
sir.
only at the time of my joining the department, the C-matrix came.
Yes,
And
sir.
after that, there was this Galva field that came, and we were just looking at it. That's all. And not too much of work were going on in this particular area in our department.
Yes,
And
sir.
so now, after hearing this lecture, I think that I should come back and attend a program on this, a complete program on this. Anyhow, thank you, sir, for making it interesting. And
Sir, for kind information, Professor Alamba George, your head of department, was my PhD examiner.
oh, fine, right. Oh, that's it. So
Yeah, I'm great to her.
oh, wonderful. Nice to hear that, sir. Nice to hear. And I request the students, if you can share your PPT with the department, that will be very useful for the students.
No problem.
I would request the students to go through every slide that has been shown. Not very difficult as you people think. It's very simple. Within minutes, within seconds, I could understand what the Galva field is. That's the way by which the lecture has gone.
Actually, I have no time to give more idea of Galva's field because of time. But Galva's field is very important, sir. You can solve many difficult problems using Galva's field.
Yeah. Yes. Within just about 5 minutes, I could understand the Galva field completely.
Okay, sir. Okay, thank you very much.
So thank you for this wonderful lecture, sir. Sadish, continue with this. All the best wishes, all my support, both physical as well as whatever way you can think of. Thank you. Right.
Thank you, sir. Thank you, professors. In fact, your blessings, we are always grateful to process. I think Professor Rajaratnam also has to say something.
Okay.
Yeah.
Okay.
Thank you, sir. Thank you very much. The lecture was so interesting because I am from Design of Experiment. My guru is Dr. Ghosh. So I am very happy to attend this session. Also, two of my students are doing PhD in the Design of Experiment. They have also joined, sir. Very wonderful lectures. Whatever things he has shown is that within a minute we can understand that one. It will be a very highly useful to the PG student. It is also in the PG level also. In the PG level, one can understand this one. Definitely they can do very good research in this area. Thank you very much. Thank you, sir. Thank you.
Thank
Hello.
you. Yeah, please.
Yes.
Hello.
Yes.
Hello,
Yes.
myself Professor H.P. Dave.
Okay. Oh, Dave.
Yeah. Hello,
Yeah.
sir. How are you?
I am fine. How are you?
Sir, I feel very proud that after so many years, once again, I got a chance to learn from you in the field of experimental of design. First, I would like to congratulate Professor Satish Kumar for such a nice lecture series in experimental design. Sir, how are you, sir?
I am fine. I just returned from USA. I was 9 months at USA.
Okay. ADM College is a head of the department
Huh.
at Vallabh Vidyanagar, sir.
Yeah.
So when you come at Vallabh Vidyanagar SP University, please do come and please try to meet me. Okay, just call me. I will meet you.
So you are staying it now, Vallabh Vidyanagar?
No, I am staying in Baroda. At present, I am with my family at Baroda.
अच्छा अच्छा.
Okay. Satish Kumar Sarji, many
Yeah.
congratulations to you.
Thank you, Professor. Thank you.
I feel very proud that I am a student of Dr. Ghosh sir, founder student,
Oh,
first bench student.
great.
And as far as my knowledge is concerned, Dr. Ghosh sir is the most eminent personality professor in the field of experimental design. I would like to
Yeah.
share my feelings with you. Thank you very much, sir. Thank you very much, sir.
Okay. Thank you.
Okay.
Yeah. Thank you. Thank you so much. Yeah. Anyone else? I think Srijit also somewhere. I think joined here. Dr. Srijit.
Sir,
Yeah. Please.
Yes,
Yeah.
sir, good sir. How are you, sir?
I am fine, sir.
Sir, I am Srijit.
Srijit, okay, this paper is very important. This paper is very important, biomedical paper, very important paper.
Yes, sir, I listened to it, and it was actually very fantastic, sir. I am really excited because once, perhaps you may have remembered that once I have asked you to explain Galois field, but at that time you have not time. You had not time, so you
Oh,
were.
sorry, very sorry, Srijit, very sorry.
Yeah, no problem, sir. I was with you that in 10 days, and on the last day, I asked you, sir, what is Galois fields? You told me that it will take 1 or 2 days to explain. But now I am very much satisfied because I am able to hear that lecture. Thank you very much, sir.
Now, I think I will explain you more one day, by phone only, by video. One day I'll explain you in detail.
Okay, very much thank you, sir. And Sadish, sir,
Yeah. Yeah. Thank you.
thank you for
the
giving me such an
participation.
opportunity.
Yeah. Thank you so much. Yeah. Several are there, I think so. If anyone, I think Rao, Srinivas Rao is there. Hello? Or Shanoja from USA, Canada. Shanoja also was there earlier, I think. Oh, yeah,
Hello.
yeah, please, Shanoja. You have
Hi,
any?
Ghosh sir. Hi, Kalyanram sir. Hi, Sadish sir.
Hi,
Yeah. Hi. Thank you so much for the wonderful lecture. It was so
thank
fruitful.
you. Thank you very
Yeah.
much.
Yeah. It's very early morning, and I think like my time I spent that early morning was really fruitful by hearing your lecture. Yeah. And Kalyanram sir, I think like almost 20 years I haven't seen you, and it's a wonderful opportunity for me to meet you in this like a Zoom meetings. Thank you very much for coordinating everything, Sudesh sir, and it was really wonderful. Thank you so much.
Thank you, sir. Thank you, Shanoja. Okay, I think if anyone please there, you can add your comments or suggestion or your questions if you have, or otherwise you can ask him through email. Yeah, Kalyanan sir has to add something. Yeah, please.
Satish, if Professor shares his PPT with you, please send it to me also.
Okay, brother. Yeah. Okay, I shall collect the PPT, and in fact, our students also very eagerly listen. Several.
Okay.
Yeah.
Thank you, sir. Sir, myself, Dr. Kimya Tinani. Very
Yeah,
nice
yeah.
question, sir, from MS University, Maharaja Sayajirao University of Baroda, sir.
What is name?
Sir, Dr. Kimya Tinani, sir.
Oh,
Sir, you know me.
okay.
You from Baroda, Kimya Tinani, sir.
No, I recognize.
Sir, my work is in inventory theory. If you remember.
Yeah, I recognize now. I recognize.
Thank you so much, sir. Thank you, Satish, sir, for giving opportunity to attend this session. Thank you, sir.
Thank you.
Very nice session, sir. Very nice presentation, sir.
Thank you so much for your your support to our activities, and also for your participation. And several professors are also there. I'm sure they can now. I think if there is no one, you can. If there is anyone, please add, or otherwise we can conclude this session. Shall I conclude? or anyone else? Okay, okay. In fact, on behalf of our department and all joined together here in this meeting, on behalf of each one of you, I extend our heartfelt gratitude to Professor Ghosh for your nice presentation and very nice. In fact, we all of you know, as an expert, giant in the area of design of experiments, and we are very lucky to have your presence and deliberations in this occasion. Once again, thanking you all for your participation, and we can have for future collaborations like or future such events we can organize. Several things we have to do. Once again, thanking you, Professor Ghosh, for your spending your valuable time with us, for giving this such a nice talk.
I am very much thankful to you, Professor Satish. You gave me this opportunity to share some of my contribution, and it is really a nice gathering with you. And hope in future also we will have this opportunity to share my other contribution to all of you and all of your friends. Thanks very much. And thanks to all my fellow members who very patiently listened my lectures, and it was not boring, I hope. Though I took some more times. It was only 1 hour, and sometimes I was feeling whether are you feeling bored or not. But hope you have not bored. And if I would have got more time, I would have covered something more also. And in future, let us see if Satish gives me this opportunity. I may sure cover some more things of my.
We can organize a workshop itself in design in future, utilizing Professor Ghosh and similar giants in the area.
Yes.
In the coming international conference, Professor Ghosh promised to organize a session with the experts in the design. Thank you, Professor.
Thank you.
Thank you all. Kalyanam sir. Thank you all. Rajaratnam sir. Shanuja, Dr. Shanuja, and other professors, all of you, please. Thank you so much. Okay, let us. Thank you, professors.
So now I'm operating.
What about the situation?
Putting off. That conference now, I'm managing. I will send the abstract of 4%.
Okay,
I'll send. I've already written them. They will send the abstract.
Okay. What about everyone, family? Everyone is okay there?
Yeah, all are okay. I just returned from USA. And I'm quarantined in home. I'm not going anywhere.
There, USA or here.
I'm in quarantine.
Okay, Professor. Okay.
But anybody, my email is there. If anybody needs some work in design of experiment with me from anywhere, my email is with you. And if they want, I can give their email. And by email also, we can do some work also. Because I'm thinking a good work using the operations, linear programming and design of experiment.
Okay.
It will be very good work.
Very good work.
Though it will be complicated, but it will be good work.
Yeah. Several students or youngsters, in fact.
Yeah, it will be very interesting. Linear programming and the design of experiment.
Design, that's.
So, okay, bye then.
Okay, bye, Professor. Thank you.
Bye to all.
Thank you, Professor. Thank you, students, for your patient listening. Thank you all. Yes.